Hello, I'm Dr. Jacob Hudis. Welcome to video 10 in my rotational motion playlist. In this video, I solve 9 challenging rotational motion problems, building on material covered in the first 9 videos. These are not beginner problems. I assume you're already familiar with circular motion, torque, angular momentum, and related concepts. I explain the physics as I solve each problem step by step. The problems start off tough and get harder. Feel free to pause the video and try each problem for yourself before seeing the full solution. Here's problem number 1. A cyclist pedals a bike with 0.7 meter diameter wheels. The pedal cranks are 0.28 meters long, the front sprocket has a diameter of 0.16 meters, and the rear sprocket has a diameter of 0.08 meters. The cyclist pedals at a steady rate of 75 revolutions per minute. Here's the cyclist on his bike. This is the front sprocket. It is a diameter of 0.16 meters. And here's the rear sprocket with a diameter of 0.08 meters. What is the speed of the chain relative to the bike frame? What's the angular speed of the wheels? What's the bike speed relative to the road? I'll solve the problem on the next slide. Question A asks us to calculate the speed of the chain. I know the speed of the chain is equal to the tangential velocity of a point on the outer edge of the sprocket. The cyclist is pedaling at an angular velocity of 75 revolutions per minute. We have to convert that to radians per second because that's the unit of science. So the angular velocity of the cyclist, which is also the angular velocity of the front sprocket because they're connected together, is equal to 7.85 radians per second. To calculate the velocity of the chain, I use the important formula tangential velocity is equal to radius times angular velocity. V equals r times omega. I know the radius of the sprocket is 0.08, and I know the angular velocity is 7.85 radians per second, so the chain moves with a speed of 6.28 meters per second. Part B asks us to calculate the angular speed of the wheels. The angular speed of the rear wheel is equal to the angular speed of the rear sprocket because they're connected together. I know V equals r times omega, so omega equals V over r. The angular velocity of the rear sprocket is equal to the velocity of a point on the edge of the rear sprocket divided by its radius. I know that the tangential velocity at the edge of the rear sprocket is 6.28 meters per second. It's the same as the velocity of the chain. So 6.28 divided by 0.04 equals 15.7 radians per second, and that's the angular velocity of the rear sprocket and the wheels. Finally, part C asks us to find the bike speed relative to the road. We know V equals r times omega, the radius of the wheel is 0.35 meters, and the angular velocity is 15.7 radians per second, so the bike moves at 5.5 meters per second. Problem number 2. A plank of mass m is placed on a horizontal surface. A solid sphere of mass big M and radius big R is placed on top of the plank. A horizontal net force F is applied to the plank. Find the maximum value of F that can be applied without the sphere slipping on the plank. Here's a plank. You can think of this as a book, and there's a spherical mass on top of the book. If you apply a force to the book, it's going to move the book forward. It's also going to move the sphere forward. However, it applies a torque to the sphere, so the sphere will rotate backward. So the sphere is not going to move forward as much as the book does. Let's look at a demonstration I did to help visualize this problem. Here's a demonstration with a book sitting on a table. Instead of a sphere, I used a can of Diet Coke. There's a piece of duct tape which marks the location of the Diet Coke relative to the book, and there's a piece of duct tape which marks the position of the book relative to the table and the Diet Coke relative to the table, and you can see they all start at the same position. As you just saw, when I pushed the book, the Diet Coke started rolling, the Diet Coke moved forward, and the book moved forward. But the Diet Coke moved forward less than the book did in the same amount of time, so the Diet Coke had a smaller acceleration than the book did. In this case, the cylinder was rolling, it wasn't slipping. If I had pushed harder, it would both roll and slip, and that's what this problem is about. I performed the demonstration a few more times. Let's watch. And here's the solution to the problem. First thing I did was draw a free body diagram for the sphere and the book. The sphere only has one force acting on it, which is the force of static friction pushing it to the right. This creates an acceleration of the center of mass of the sphere. I'm going to call this A1. And the friction force puts a torque on the sphere, so it has a counterclockwise angular acceleration. The book has 2 forces on it, the applied force forward and the frictional force backwards. The forward force is bigger than the frictional force backward, but that's not drawn well in this picture. And the book has an acceleration A2. The acceleration of the book is different than the acceleration of the sphere. Now I'm going to set up Newton's second law for the sphere. Net force equals mass times the acceleration of the sphere. The net force acting on the sphere is just the force of friction, mu s times the normal force, mg. And this tells us that A1, the acceleration of the sphere, is equal to mu s times g, where mu s is the coefficient of static friction. The net torque on the sphere is equal to I alpha. The frictional force causes a counterclockwise torque on the sphere. The torque is equal to force times radius. It's the force of the friction times the radius. The moment of inertia of a sphere is 2/5 mr squared. This allows us to solve for alpha, the angular acceleration of the sphere. and it's 5/2 mu sg over r. Newton's second law for the plank says the net force on the plank equals mass times the acceleration of the plank. The net force on the plank is the forward applied force minus the force of friction. This gives us an equation which allows us to solve for A2, the acceleration of the plank. For this particular problem, the acceleration of the sphere and the acceleration of the plank are different. The sphere has a smaller linear acceleration than the plank does. The condition for rolling without slipping is that the acceleration of the sphere equals the acceleration of the plank minus r alpha, how much the plank rotates backwards. This is a key equation in this problem, and it's something you should think about and make sure you understand. So now I can substitute values into this equation. I know A1 is equal to mu sg, so A1 equals A2 minus r times alpha, and this is alpha. This is a simple algebraic equation, and it allows us to solve for A2. The acceleration of the plank equals 7/2 mu sg. Now let's come back to Newton's second law for the plank. Net force equals mass times the acceleration of the plank. This is the net force acting on the plank, the forward applied force minus the backward force of friction. This equals mass times A2. But now we know what A2 is. We just solved for A2. A2 is 7/2 mu sg. So I can replace this A2 with 7/2 mu sg. This simple equation allows us to solve for F. This is the threshold force. If you put a force larger than this, the sphere will begin to slip. It will roll and slip. But any force less than this value, the sphere will only roll, and it will roll without slipping. All right, problem number 3. This is a short one. A 70,000 kilogram aircraft is flying in a vertical loop with a circular path of diameter 200 meters. At the moment it's heading straight downward, its speed is 60 meters per second and the downward acceleration is 10 meters per second squared in the direction of motion. What's the magnitude of the total force acting on the aircraft? What angle does the net force make with the horizontal? There's a jet, it's flying in a vertical circle. At this point in time, it's headed straight downward. So there's a force of gravity which pulls it downward. But it's also flying in a circle, so there has to be a force towards the center of the circle, a centripetal force, mv squared over r. The pilot can adjust the wing, and that produces a lift force towards the center of the circle when the air flows over the wing. And here's the solution. The jet has a force towards the center equal to mass times centripetal acceleration, mv squared over r. We're given all this information, so the centripetal force is 2.52 times 10 to the 6 newtons. The tangential force, or the downward force of gravity, is equal to mass times the acceleration of gravity. We'll call that -10. And that equals -7 times 10 to the 5th newtons. The net force is in this direction. It's in the direction of the net acceleration scaled by the mass. To calculate the net force, we use the Pythagorean theorem. The net force is the square root of the force in the x direction squared plus the force in the y direction squared. And that's 2.62 times 10 to the 6th newtons. And then the angle theta is the inverse tangent of the y over the x component, and that's -15.4 degrees. Problem number 4. A yo-yo of mass m, moment of inertia I, and inner radius little r is released while tied to a string. As it falls, it rolls without slipping around the string. Find its acceleration. Here we have a yo-yo. It has outer radius big R and an inner core with radius little r, and there's a string wrapped around that. The string produces a tension force upward, and that produces a tension torque, which causes a counterclockwise rotation. And we also have gravity acting at the center of mass of the object. To solve this problem, I'll begin by setting up Newton's second law for translation. Net force equals mass times acceleration. There are two forces acting on the yo-yo, tension upward and gravity downward. This equals mass times acceleration. Next, I apply Newton's second law for rotation to the yo-yo. Net torque equals I alpha. Recall, these are the standard sign conventions. Counterclockwise is positive and clockwise is negative. The tension force puts a counterclockwise torque on the yo-yo. It's equal to little r times the force of tension times the sine of 90. So RT equals I alpha, and alpha is acceleration over r. This equation allows me to find an expression for tension, IA over r squared. I can then come back to Newton's second law for translation, bring the MA to the left side of the equal sign, and I get T minus mg minus MA equals 0. I can replace the T with this expression that we found earlier, and that leads to this equation. This equation has acceleration in two of the terms. It's a simple algebraic equation to solve. The solution is here, and the result is that the acceleration of the yo-yo is mg divided by I over r squared minus m. This will always produce a negative acceleration, which makes sense. The yo-yo is moving downward, and that's because I over r squared is always less than m. Can you explain why that's the case in the comments? As the yo-yo descends, it unwinds the string, creating an upward tension and counterclockwise torque. At the bottom, it receives an impulse, reversing its spin to clockwise. The tension remains upward, but the yo-yo now ascends, converting rotational kinetic energy to potential energy. Problem number 5. A bowling ball with mass 3.5 kilograms and radius 0.117 meters is thrown down a lane at 8.4 meters per second. The coefficient of kinetic friction between the ball and the floor is 0.25. At first, the ball slides, then it starts to roll without slip. Questions. What is the angular acceleration while sliding? What is the linear acceleration while sliding? How long does it take to start rolling without slipping? How far does the ball slide before it rolls? What's its final speed when rolling begins? Now I'm going to show you an animation to visualize this problem. Here's a bowling ball, and initially it only has translational velocity. There's no rotation. As the object slips along the surface, the kinetic friction between the object and the surface exerts a torque that causes the object to begin rotating. When the rotational velocity gets big enough, the object will roll without slipping. So here the object is rolling and slipping, and now it's rolling without slipping. Now let's solve the problem. What is the angular acceleration while sliding? I started by drawing the free body diagram on the bowling ball. There's the force of gravity downward, the normal force upward, and a force of friction which opposes the motion. We know net torque equals I alpha, so alpha, the angular acceleration, is equal to torque over I. I, the moment of inertia of a sphere, is 2/5 mr squared. The torque on the bowling ball is equal to the force of friction times the radius. The force of friction is mu times the normal force, mg, so the torque is mu mgr. Plugging in expressions for torque and moment of inertia, I find the angular acceleration is 5 mu kg over 2r, and for this particular problem, that's 52.4 radians per second squared. 2. What is the linear acceleration while sliding? I know net force equals mass times acceleration, so acceleration is force over mass. The force acting on the bowling ball is the force of kinetic friction, and this tells us that the linear acceleration is mu k times g. When we plug in values, that gives 2.45 meters per second squared. How long does it take to start rolling without slip? I know from the kinematic equations that v final equals v initial plus acceleration times time. In this case, the acceleration is negative, and we found on the previous slide the acceleration is negative mu kg. I also know that omega, angular velocity, equals alpha, angular acceleration times time. I found angular acceleration on the previous slide, so this is an expression for omega as a function of time. The condition for rolling without slipping is the velocity of the center of mass is equal to omega r. I'm going to replace this velocity with omega times r, and that equals v initial minus mu kgt, and then some basic algebra leads to this equation, and this allows us to solve for time. Plugging in the values gives 0.98 seconds. How far does the ball slide before it rolls? Displacement equals v initial t plus 1/2 at squared. In this case, the acceleration is negative, and we know all of these values. V initial was given, we just calculated time. Plugging in all the values gives 7.06 meters. What is the final speed of the ball when rolling begins? I know V final equals V initial plus AT. We have all this information. V final equals 6 meters per second. Once the ball is rolling without slipping, the kinetic energy of the center of mass is 63 joules, and the kinetic energy of rotation about the center of mass is 25.2 joules. Problem number 6. The density of the Earth at a distance r from the center can be approximated by this model. Density is mass per volume, and this is a model that can be used to represent the density of the Earth. 14 minus 11 little r over big R. Little r is a point from the center of the Earth somewhere inside the Earth, and big R is the radius of the Earth. And then it's multiplied by 10 to the third, and the units of density are kilograms per meters cubed. Show that this density function leads to a moment of inertia I equals 0.33 mr squared. To solve this problem, we're going to break the Earth up into many small spherical shells. We're going to calculate the moment of inertia of each spherical shell and sum them all up to give the total moment of inertia of the Earth. The moment of inertia of a spherical shell is 2/3 mr squared. The moment of inertia of an individual subshell of the Earth is 2/3 dmr squared. dm is the mass of one of these shells. dm is equal to volume times density. The volume of the shell is 4 pi r squared dr. This is the area of a sphere, and you multiply by dr a small thickness. To calculate the total moment of inertia, I sum each individual moment of inertia by taking the integral from 0 to r of this expression, where I replaced rho with the given expression for the problem. This is a very simple integral to compute. The work is shown here, and we find the moment of inertia equals the constant 8 pi over 3 times 10 to the third times the radius of the Earth to the fifth times 0.967. We also need to calculate the mass of the Earth using the density function provided. To do this, we calculate the mass of each one of these individual spherical shells and sum them all up. And that's the integral from 0 to r of rho dv. This is rho, and dv is 4 pi r squared dr. This is another easy integral to compute, and we find that mass is equal to 4 pi times 10 to the third r cubed times 1.97. Moment of inertia is always proportional to mr squared. If I take the moment of inertia divided by mr squared, I'll get the proportionality constant. This is the moment of inertia that we just calculated, and this is mr squared. We took this mass and multiplied by r squared. After canceling out the r's and simplifying the expression, we find the proportionality constant is 0.330. Using this model, the moment of inertia of the Earth equals 0.33 mr squared. Problem number 7. The polar ice caps can be modeled as two thin, flat disks with radius 6 times 10 to the 5th meters and a total combined mass of 2.3 times 10 to the 19th kilogram. Earth's moment of inertia is the sum of its own inertia and the inertia contributions from the ice caps. If the ice caps melt due to global warming, the water would redistribute into a thin spherical shell at Earth's surface. Question: if the ice caps melted, determine how much longer Earth's rotational period would become. Earth is a massive sphere, and right now it has polar ice caps. There are two disks of ice near the North and South Pole. If these ice caps melted, there'd be a layer of water that would form on the outside of Earth. This question asks us how much longer a day would be if this redistribution of water occurred. To solve this problem, we use conservation of angular momentum. Angular momentum initial equals angular momentum final. And remember, angular momentum is equal to I, moment of inertia, times omega. The moment of inertia of a solid sphere is 2/5 mr squared. The moment of inertia of a disk is 1/2 mr squared. And the moment of inertia of a thin shell is 2/3 mr squared. The Earth is a sphere, and the moment of inertia of the Earth without the ice caps is 9.72 times 10 to the 37 kilograms meter squared. The moment of inertia of the ice initially is equal to the sum of the moment of inertia of these two ice disks. That's equal to 1/2 times the combined mass times the radius squared, and that's 4.14 times 10 to the 30th kilograms meter squared. If the ice melts, the water redistributes into a thin shell. The moment of inertia of the final thin shell would be 2/3 times the mass of the ice times the radius of the Earth squared, and this is equal to 6.22 times 10 to the 32 kilograms meter squared. So the moment of inertia of the Earth increases. Conservation of angular momentum tells us omega final over omega initial equals moment of inertia initial over moment of inertia final. Moment of inertia initial equals the moment of inertia of the Earth plus the moment of inertia of the ice disks. Moment of inertia final equals the moment of inertia of the Earth plus the moment of inertia of the spherical water shell. Plugging in the values, we find the final angular velocity is equal to 0.1 times the initial angular velocity. Angular velocity is defined to be 2 pi over t. So angular velocity final is 2 pi over t final, and angular velocity initial is 2 pi over t initial. T initial is 24 hours, the amount of hours in a day, and this is 86,400 seconds. When we plug in the values, we find that the final period is 86,451 seconds. Delta t is t final minus t initial, so if the polar ice caps were to melt, we get 51 more seconds in the day, and a lot of the land on Earth would be flooded.
I changed voices on my microphone. We're running out of time, so I'm going to skip problem 8. And here's the solution. Problem number 9.
And finally, problem number 9. At a particular instant, a force F acts on a 0.25 kilogram object located at a position R with a velocity v. Relative to the origin and using unit vector notation, determine the object's angular momentum and the torque exerted on the object. I plotted the vectors. The blue vector is the position vector, this vector is the force vector, and the velocity vector is pointing back this direction. Torque is equal to R cross F. To compute the cross product, we use the determinant. This is an important formula to calculate the cross product of two vectors in three-dimensional space. If you don't know it, you should memorize it. When you compute the torque, this is the answer. This is the final answer when you plug in numbers and compute the torque. To calculate the angular momentum, L equals R cross mv, or m times R cross v. I can put the m out in front of the determinant, calculate the cross product, and it equals to 0. This makes sense because the position and velocity are 180 degrees apart. They're on the same line.
AcePhysics.org. Math and physics tutoring with Dr. Hudis.